Okay, let's go ahead and answer this first one. So we've got to find volume. We've got moles. We've got pressure. I have a temperature. I'll just take the temperature 273, 317 K. Just do that right away. How do we start this problem? Dana. And how do I set it up? Like that. Okay. Wait, no, I'm not. Oh yeah, my bad. 0.08206 liter atmosphere mole Kelvin. Why am I setting this problem up like this? Because I want to find liters because I'm looking for volume, and now I've got the liters right where I want it. So I'll get rid of everything else. I'll put 5.6 ATM here, and I will put 4.4 mole here, and I'll put 317 K there, and then I can get the ATMs to cancel, the kelvins to cancel, the moles to cancel, and then I've got an answer of some kind. 0.08206 times 4.4 times 317 divided by 5.6, and I get 20.4 liters. 20.4 liters. All good? What would the volume be for this sulfur dioxide gas? All right, so first off, let's do 273, 292, and probably 15.999, clear, 15.9994 times 2 plus 32 point, what is it? What's sulfur's molar mass? Who's got a periodic table? 0.066. Okay. So, how am I starting this? Exactly the same way I started the last problem, right? Because I'm looking for a volume. So I'll go ahead and throw down 0.08206 liters times atmospheres divided by moles and Kelvin. And I've got 292K, and I've got 2.12 ATM, and I've got 64 grams SO2. And then if I look on the table, I can get 64.0648 grams of SO2 per 1 mole of SO2. And if I do that, then I can get my Kelvin to cancel, my ATM to cancel, my grams to cancel, and my moles to cancel. And so then I just have my liter unit. And let's see, what do we get? 0.08206 times 292 divided by 212 times 64 divided by 64.0648. Get 11.3 liters. Okay, so we have this flask. It's got 56 grams of nitrogen and 12 grams of helium, and the pressure due to the nitrogen is 4 atm. What's the total pressure in the container? Okay, so if I take 56 and I divide it by 28, I get 2. Why am I doing that? Sorry, I should do this. Why do I know to divide by 28? What's pressure due to? Gas pressure is due to what? Number of particles. That's it. the number of particles. If I've got the same gas, if I've got two gases in the same container, the only thing that matters about how much pressure they exert is how many of those particles there are. So I've got about 56 grams, and the molar mass of N2 is about 28. So then if I divide the 56 by 28, I get about 2 moles of N2. And if I've got about 12 grams of neon, and neon's mass is about 4 grams for 1 mole, so I've got about 3 moles of neon. Is it neon? Sorry, not neon. Neon? Helium, my bad. I got about 3 moles of helium in the container. And I am being told that the nitrogen's pressure, this 2 moles is equal to 4 atm. So what's the pressure of the helium going to be? 6? You okay with 6? How'd I get 6 out of that? Every single ATM is equivalent to how many moles in this particular case? Let me rephrase that. Every mole is equivalent to how many ATM in this case? Now put your fingers up. 2. So I have 2 moles of nitrogen gas, and what's the pressure I get out of that? 4 atm. So what if I had 1 mole of nitrogen gas? What would the pressure be? 2. So every single mole of gas provides what? 2. N2. Because it's a diatomic. So this is going to be 6. You could just do cross multiply. 2 divided by 3 is equal to 4 divided by 6. So the answer to this is what? 10. The pressure, the total pressure in here is 10 atm. The point of this question is for you to realize that the only thing that matters for 2 gases in the same container about pressure is how many of them that there are. And so I know there is 50% more helium in the container, so the pressure due to the helium is going to be 50% more than it is due to the nitrogen. Yep, those are the only 2 gases in the container. Electron configuration for fluorine, chlorine, and bromine. All right, so fluorine, 1s2, 2s2, 2p5. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. And bromine, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. What do they all have in common? Location, right? On the table, they're all P5. It's just one right underneath the other, and you would expect that because it's fluorine, chlorine, and bromine in the halogen column, one right after another. We have questions about this one? No? Energy level diagram for bromine. Okay, so 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. So 1, 1, 1, 1, 1, 2, 3, 1, 2, 3, and 1, 2, 3, 1, 2, 3, 4, 5. So 2 and 2 and 2 and 2 and 1 and 1 and 1 and 2 and 2 and 2 and 1 and 2 and 1 and 1 and 1 and 2 and 2 and 2 and 1 and 2 and 1 and 1 and 2 and 2 and 2 and 2 and 1 and 1 and 1 and 2 and 2. That look good? Questions about that? You said 2p6?
Like, no, what I'm trying to say is you're going off the top.
I'm
Yeah.
I'm going off the periodic table. I'm just thinking about it in my head as I'm doing this.
I mean, I'm confused on how to set up if you're using different elements, like just saying the charges and whatnot. How are you determining that it only goes up to 3D or whatever?
Well, in this particular problem, I'm looking for bromine, right? That's the electron configuration for that element right there. So when I'm filling up electrons into energy levels and sublevels, where do the first electrons go? How do you know that? By looking at this table. What does this constitute? That's the 1s. And how many electrons fit in it? 2. So how many electrons do I have to deal with? 35 total electrons. So I've used 2 of my 35. So now what? Here's 2s, and that's 2 more electrons, right? So I've used 4 of my 35. Then the next place I go is here, and this is 2p, and so that's 6 more of my electrons, so I've used 10 so far. 3s is 2 more, so 12, and then 3p is 6 more, so that's 18 of my 35. 4s, because that's the next thing I run into. And then what's this right here? That's the 3d, and that's 10 more electrons. And then my last 5 electrons go in the 4p. So when I was writing those electron configurations and when I was writing those energy level diagrams, this is what I was thinking of in my head. How many electrons I go to, which block I hit next. So as I'm doing this, I'm thinking, I'm going to throw 2 electrons here and 2 here and 6 and 2 and 6 and 2 and 10. And then I ran out and I've only got 5 more left and that's the end of it. What are we doing here? Why does sodium atoms react much more violently than magnesium atoms, even though they're alongside each other on the table? All right, so I've got a sodium and I got a magnesium, and it's 1s2, 2s2, 2p6, 3s2, and I got a sodium, 1s2, 2s2, 2p6, 3s1. So you guys held magnesium in your hands in lab. Remember that? Right before you lit it on fire? You like pulled it out of that. It was like a little ribbon piece of metal, and you cut it and you cleaned it up and then you lit it on fire. Could you do that with sodium? No, it would start reacting immediately. It would definitely burn you, catch whatever water on your skin was on fire. It wouldn't be comfortable. So obviously it's much, much more reactive. Why? What about it? Why? Yeah, because there's only one, it's easy to get rid of. And so easy to get rid of means very violently reactive. So when we did our initial definition for chemistry, what was the second part of it? Study of properties of matters and actions of electrons. This electron right here has a lot of action because it just needs to disappear. Sodium wants it to just go away. And so it's very easy to give away 1 electron. Magnesium absolutely wants those 2 electrons to go away. And when you pulled that magnesium off of that little ribbon, that little spool, was it nice and clean? I had to rub it down with steel wool. Why? It had already reacted. What did it react with? Yep. So you were rubbing this, which is rusted magnesium, off of the top of the regular magnesium. And so I wanted access because that rusted magnesium wasn't going to burn. That's actually what we were making. So what I needed is to get rid of that stuff so I can get the magnesium. Well, it rusted, and it rusted fairly easily, but not nearly as easily as the sodium would have rusted. And it's because of that whole kitten thing, right? What do I mean by that? Easier to give away 1 kitten than it is to give away 2 kittens. So it's easier to give away 1 electron than it is to give away 2 electrons. So if I can give away 1 electron, it happens very fast. And in chemistry sense, that fastness always manifests itself in something a little bit more violent. So the speed dictates how the reaction is going to behave. So on this one, you should be saying something about the fact that even though they're right next to each other, the sodium has one electron to get rid of. And it's very easy to get rid of one electron and significantly more difficult to get rid of 2 electrons. Yes?
So looking at the periodic table and elements on it, if the element only has like one electron, we'll know that one's super reactive.
And so the column that sodium is in, everybody in that column is very reactive, right? That video we watched, that Brainiac video of lithium catching on fire and sodium catching on fire and potassium catching on fire and then rubidium and cesium exploding that bathtub. So it gets more and more violent, but all of them react violently
All the elements on the periodic table.
in that column.
Oh yeah, it's
All right, write a balanced chemical reaction for the combustion of octane with oxygen to produce CO2 and dihydrogen monoxide. So I've got C8H18 plus O2 yielding me CO2 plus H2O. Balancing it, what do I need? What's the problem with this problem right off the bat? Okay. I have an odd number of oxygens. That is a problem for me because I've got an even number of oxygens over here and this is automatically giving me an odd number. So what should you do? Fix that, okay? So if I put a 2 here, that's not super helpful. That's usually what we do, is to just double that thing. But I've got a bunch of other stuff going on. So I'll just run through the balancing and we'll think about this as we're doing it, that we're going to end up having to deal with this odd number of oxygens. So if there's 8 over here, I'm going to put an 8 here, and so that balances out my carbons are now balanced. And there's 18 hydrogens on the left, and if I put a 9 here, what's that do for me? I got 18 on both sides, but I still have an odd number for the oxygen, right? So now what should I do? So if I take this 9 and turn it into an 18, that oxygen is now a double. The problem is over here, now I've got 36, there's 36 hydrogens on this side, so I got to fix that by putting a 2 right there. And then that messes up the first thing that I did, so I got to put a 16 here for my CO2. All right, that? All right, so now what about my oxygens? So this is 16 and 2 is 32, and then the 18 gives me a total of 50. So if I put a 25 right there, now my oxygens are balanced. Everybody's balanced out. So most of you, I think everybody in this room except for Gideon used this today, right? Why is Gideon the only one not using this? Because he rode his bike. So he was not burning octane, the fuel that's in your gas tank. So I've got 25 grams of the octane and 150 grams of oxygen, and I'm going to allow them to react, and I want you to tell me what's left in the container. Okay, so this is a limiting reagent problem, so what's the first thing we need to do with this? Okay, but 2 of them, right? So I'm going to go 25 grams of C8H18, and I'm going to go 150 grams of O2. What are these 2 calculations going to do for me? They're going to tell me which one's going to run out first. So to do that, I need to make sure that they both end with the same substance. Doesn't matter which. Sir, I'll put water's fine. So the mass isn't important. What's important for me is moles of octane. So what do we got here? No, don't do that. 12.011 times 8 plus 1.00795 times 18 plus you 114.5 0.231. Where do we get this number from? 8 carbons and 18 hydrogens. Okay, so what's this first step do in both of these calculations? I'm getting rid of the grams, but I'm counting how many octanes and counting how many oxygens are actually in this container. So I look up at the balanced chemical equation, and for every 2 octanes, 2 moles of C8H18, there are 18 moles of H2O. And then for every 25 moles of O2, there's 18 moles of H2O. And then for every 1 mole H2O, 1 mole H2O, grams H2O, grams H2O. So 15.9994 plus 1.00795 times 2. Get 18.0153, 18.0153. Okay, so that times 18 divided by 2 divided by 114 times 25. So 35 grams H2O. 150 times 18 times 18.0153 divided by 25 divided by 31.9988. 60 grams H2O. Okay, what do we know? The octane's going to run out first. So my limiting reagent in this problem is going to be my 25 grams of octane. Great. The moment I've made 35 grams of water, what happens? It stops reacting. So I can never make 60 grams of water. Why? As soon as I hit 35 grams of octane, I don't have any more octane, so I can't make any more water molecules. Okay, so what I know right now is there's going to be it has to be on the same on both sides, including the leftover stuff. So what I know right now is I've got 0 grams of octane left in my container. I know I've got 35 grams of water in my container. So now what I want to know is, yep. Yeah, there's no other way to do it. So what I've done down here, this thing down in the bottom is going to look exactly like what I have up at the top, to the halfway point. And now I already know how much water I'm going to make, so now I'm going to do a conversion over to figure out how many grams of CO2 I'm going to make. So now this is going to be 16 mole CO2, 1 mole CO2, grams CO2. So it's 12.011 plus 15.9994 times 2 equals 44.0098. 8 divided by 114.23 times 25. You get 77 grams CO2. So now I also know that there's going to be 77 grams of CO2. So I know that I have actually created 112 grams product. I've created 112 grams of my products. I put 175 grams in my container. So what do I know? So if I take 175 minus the 112, I get 63 grams of leftover oxygen. And so now these two numbers equal 175 because they have to. I put 175 grams of stuff in the container. I have 175 grams of stuff in the container when I'm finished. It's just different stuff. Well, some of it's different stuff.
So when you find the limiting reagent, you go back and you do the second part of the equation when it's like a.
So what if there were 3 products? I have to do with every single one of these problems, I have to do this immediately, right? I have to do these top 2 because I have to figure out which one is going to run out first. And then as soon as I do that, then I have to do a number of railroad tracks with the one that's going to run out first equal to the number of products. So in this case, I did this one right here twice. How come? Because I had 2 products. So I needed to do it once for each product. If there were 3 products, I'd need to do it a 3rd time. If there were 10 products, I'd need to do 10 railroad tracks with the octane. Probably not, except for yours. Because you missed a week.
On the tester, you're gonna put something like just say octane, because I had to look up.
I know, I wouldn't do that to you. I absolutely would not do something like, hey, here's the exam. Tell me what dimethyl chloroethene is. No, nothing like that would happen. I only did that on this exam or on this homework because I knew you could Google it in 3 seconds and figure out exactly what the formula was. Destiny?
When I read, like, the beginning, Peter balancing equation, he said, like, write a balancing equation for octane. I'm just confused on how you get 6 carbons and 18 hydrogen. How did you know that it was carbon and hydrogen? How was you stuck on how to write that? You know,
How did I know that this was C8H18?
yeah.
I expected you to Google it.
I tried to Google it, but it wasn't working. Oh, no.
Yeah, because I'm guessing if I Google,
No, I'm serious.
Chemical,
You
you
know,
know
you're
your octane and it comes right up. That's kind of on anything.
and really the only reason I picked it is because you didn't actually even need to Google it. You could have just done what? Could have gone to a gas station. Looked on the pump on the gas station. It would have said C8H18.
And then that's the formula for octane, and then we were trying to make it balanced, combining the octane, and then that's where it is, and that's the formula.
Yeah.
You can tell us exactly what